In this video, we will talk about alternating series. So alternating series are series whose elements are changing their sign for each consecutive term. Okay. So far, we did two tests. That was the integral test and the comparison tests, and both of them, as you remember, were applicable to series with positive terms only. Okay. Well, then I said, well, what if the whole sum is consisted of negative terms only? Well, then you just factor -1 for the whole series, put it in front of the Riemann sum, and then you deal with sum with positive terms only again, right? But now the question is, how are we going to determine if a series is convergent or divergent if the series looks like this: negative or b1 minus b2 plus b3 minus b4 plus b5 minus and so on, where bn is positive for each n. Okay, or that can be written as, this can be written as the sum of an being equal to bn, okay, and we said bn is going to be positive, times a -1 to power n minus 1, okay, and depending on n, this part here just alternates the sign in front of bn. Okay. So let us put two more conditions here. Let us say, on the top of that, let us assume that bn is a decreasing sequence, okay, which means bn is greater or equal to bn plus 1, and let us assume that the limit of bn as n goes to infinity is equal to 0. Okay, let's give let's say graphical explanation what would happen if this is consistent. So if this is satisfied, let's see what will happen. So how much is going to be a1? Well, we know that a1 is just going to be b1, right? So if we start, let's say, from 0, okay, how much is going to be the first partial sum? Well, that's just this distance, b1, right? So that's s1. Okay. How much is s2? Well, s2 is equal to a1 plus a2, okay, which is going to be equal to b1 minus b2. So look at this. The second partial sum is less than the first partial sum, because remember that bn are all positive. So here I have a difference of two positive terms. So that means I'm coming back, right? Because b2 is positive, bn is positive for each n. b1, now I'm here, b1, because b1 and s1 are the same, b1 minus b2, so minus some value b2, brings me here. This is s2. Okay, obviously from this graph, s2 is less than s1, right? Okay, how much is the third partial sum? s3 is equal to a1 plus a2 plus a3, or that's b1 minus b2 plus b3. Sorry, b3. Now this here is nothing else but s2, right? So s3 is s2 plus some positive constant b3. So now that means that again I move in this direction, right here. This is b3. So this is s3. Okay. s4 on the other hand is going to be s3 plus b4. Sorry, plus a4, my bad. and A4 is negative B4, so that's S3 minus B4. This is going to be B4, positive number with negative in front. That means we're coming back. This is S4. Okay? So as we can see, right, because of the fact that Bn is a decreasing sequence, this is how the partial sums are going to react, okay? And then this is going to be S7, S8, S9, S10, and so on, up until we reach some value S. So these, the odd partial sums are going to approach S from here, and the even partial sums are going to approach S from here, okay? So let us prove this. So we're assuming, again, I'm just, the assumption is Bn is greater or equal to Bn plus 1, and limit of Bn is equal to 0 as n goes to infinity. So let's see how this is going to help us formally prove the fact that under these conditions the alternating series is convergent. Okay, so S1 is equal to, S2 is equal to B1 minus B2, and as we saw, that's greater than 0. Why it is greater than 0? Because I'm subtracting two positive numbers such that B2, the consecutive number, is always less than the previous one. Okay, S4 is going to be equal to B1 minus B2 plus B3 minus B4. B4, this one I already know is positive. This one is also positive. Moreover, this here is S2 plus something that's positive, B3 minus B4. So that will be greater or equal to S2. Okay, one more. S6 is going to be equal to S4 plus B5 minus B6. This is positive because B6 is always less than B5 by the assumption, right? So this is going to be greater or equal to S4. And as we go on like this, we'll see that this subsequence of even partial sums, S2n, is going to be equal to S of 2n minus 2 plus B of 2n minus 1 minus B of 2n. B of 2n is the term after B of 2n B2n minus 1, so that's positive. So this one is going to be greater or equal to S of 2n minus 2. So what do we have here? From here we can see that the subsequence S of 2n is increasing, right, or simply monotonic. Okay. But notice also that S of 2n, this one, can be written as B1 minus B2 minus B3 minus B4 minus B5 minus and so on, where each of these, right, are positive. This is positive, this is positive, and so on. So basically S of 2n is some positive value B1 minus positive terms, which means it implies that S of 2n is less or equal to B1. Or on the other hand, from here it means that this subsequence S of 2n is bounded, right? Because it's also greater or equal to 0. So by the monotonic sequence theorem, this subsequence S of 2n is convergent. That means it has a limit, right? The limit exists, and now let's just call that limit. Just give me a second here. Let's call that limit S. So limit of S of 2n has a limit, and we just call that limit S as n goes to infinity. Okay? So what we have proved? We have proved that this sequence S2, S4, S6, and so on, as n goes to infinity, approaches to some value S. Okay? If we are able to show that the subsequence of odd partial sums, S1, S3, S5, and so on, approaches to the same limit, then we can conclude that Sn, right, the sequence of partial sums, approaches to the limit S. Okay, so let's do that. Let's check whether we are able to show that S of 2n plus 1, the sequence of even partial as the odd partial sums, is also convergent. As a matter of fact, not only convergent, but converges to this value here, the value S. Okay? So I want to find the limit as n goes to infinity. Okay? That's equal to the limit. What is the what is S of 2n plus 1? It's S of 2n plus b of 2n plus 1 plus the next term. Okay? By properties of limits, separate the sum, express it as sum of limits. Okay? This limit here, we show that converges to some value that we call it S. Plus, and now look at this condition here. The limit of bn as n goes to infinity is 0, which means that the limit of 2n plus 1 is 0. And what we have shown, that the limit of S of 2n plus 1, which means the subsequence made out of the odd partial sums, converges to the same value S. So we conclude that the alternating series sum of an, which can be written as negative 1 to power n minus 1 times bn as n starts with 1, is convergent as long as bn is decreasing and the limit of bn as n goes to infinity is equal to 0. This here is nothing else but the alternating series test. So if you see an alternating series, all you have to do is show that this condition is satisfied and this condition is satisfied. That's it. Well, the good news is that it's very easy to recognize an alternating series. Determine if the following series is convergent or divergent. negative 1 to power n, 1 over n. It goes from 1 to infinity. This part right here, negative 1 to power n, tells us that we're dealing with alternating series. So what do we have to do? You have to figure out how much your Bn is. Well, this here is your An, right? Bn is equal to absolute value of An, which means this absolute value just deals with the alternating part, makes every term positive. So this is just 1 over n. Okay, first show that Bn is greater or equal to Bn plus 1. We need to show this. 1 over n is greater or equal to 1 over n plus 1. Just cross multiply and you're done, right? N plus 1 is greater or equal to n. Just by cross multiplication, you can even cancel this if you want to show what is obvious, that 1 is greater or equal to 0. And 2, the limit of Bn. So what we have shown? We have shown that Bn is decreasing. The limit of Bn as n goes to infinity is equal to the limit of 1 over n as n goes to infinity is equal to 0. So we have shown the two conditions of the alternating series test. They're satisfied, right? So now you can just write by the alternating series test our sum is convergent. Be careful. We learned that the sum of absolute value of An, which is nothing but the sum of Bn, is divergent. That's the harmonic. But if we're talking about this series, which is an alternating series, all we have to deal is with Bn and show that these two conditions of that sequence are satisfied. Okay? So let's do a few more examples of this. Question negative 1 to power n minus 1 and starts with 1 to infinity n over n squared plus 1. Okay, so this whole thing is your An, and from here Bn is the expression just without the alternating part, right? Bn is equal to absolute value of An. This is the positive part only. Okay, so what do we have to show? That Bn is greater or equal to Bn plus 1. Here, you can do it this way. Bn plus 1 is greater or equal to, 1 over n squared plus 1 is greater or equal to, how much is going to be Bn plus 1? n plus 1 over plus 1 squared plus 1. And then cross multiply and you'll have n times n plus 1 squared plus 1 greater or equal to n squared plus 1 times n plus 1. Okay, and then expand this n squared plus 2n plus 1 plus 1 is show that it's greater than n cubed. N squared plus n squared plus n is n cubed, n squared plus 1 is n, 1 plus n is n plus 1, and this is n cubed plus 2n squared plus 2n greater or equal to n cubed plus 2n plus 1. And then if you want to make it obvious, right here 2n squared is greater or equal to 1 for each n greater or equal to 1. Okay, so we have shown that this condition is satisfied, and 2, the second condition is even easier. This is equal to 0. So by the alternating series test, sum of negative 1 to power n minus 1 n over n squared plus 1 is convergent. So as you can see, all you have to do is identify how much is your bn, and then for that bn just show these two conditions, right? That the limit of bn is 0 and that bn is decreasing. Okay, so let's do more examples. 3, sum of negative 1 to power n e to power 2n over 7 minus e to power 2n. Sorry, let's put it plus. Okay, then goes from 1 to infinity. Again, as I said in the previous lectures, always keep it in your mind the test for divergence. And also know that if limit of bn is not 0 as n goes to infinity, then limit of negative 1 to power n times bn will also not be equal to 0 as n goes to infinity, right? And if the limit of an doesn't go to 0, then by the test for divergence we can conclude that this is divergent. So always mentally check what happens with this limit. If it is not 0, okay, then by the test for divergence we conclude that this is divergent, right? So bn is equal to e to power 2n over 7 plus e to power 2n. Okay, so the limit of bn is equal to the limit of e to power 2n over 7 plus e to power 2n. I'm going to leave it to you to confirm that this is 1, which implies that the limit of negative 1 to power n times bn, which is nothing else but the limit of an, this is an, is not 0, then by the test for divergence we conclude that the sum of negative 1 to power n e to power 2n over 7 plus e to power 2n is divergent. And let's do one more example. Let's say 4, sum of negative 1 to power n square root of n squared plus n over n to power 3 over 2. Okay, from here bn is equal to just the part of the expression without the alternating part, so n squared plus n over n to power 3 over 2. Okay, limit of bn is equal to the limit of square root of n squared 1 plus 1 over n, and I'm factoring n squared within the root, over n to power 3 over 2. This is equal to the limit, since n stands for positive integers only, square root of n squared is just positive n, just n, square root of 1 plus 1 over n to power 3 over 2. Now you cancel this term with 1 n in the denominator, and then you send n to infinity, which makes this guy go to 0, so this approaches to 1 over n as n goes to infinity, and this is 0. So we have shown that the limit of bn is equal to 0, and now we have to show this more difficult thing, right, that bn is decreasing. If you can sense that you cannot do this inequality that easy, just define a function square root of x squared plus x over x to power 3 over 2 and show that f prime of x is less than 0. In that case, you have shown that this function, which means this sequence, is decreasing, right? So f prime of x is equal to x to the power of 3 squared, the denominator. Then the numerator is 2x plus 1 over x squared plus x times x to the power 3 over 2. minus, this is how much? 3 over 2 x to the power 1/2 square root of x squared plus x, which is equal, I'm going to continue here, 2 times x cubed square root of x squared plus x. So I bring everything under common denominator and I put the denominator in the numerator down here. So I have 2x plus 1 x to the power 3 over 2 minus 3 over 2, without the 2, sorry, so without the 2, minus 3 square root of x times x squared plus x, okay? And then all I have to show that this is negative, so here it's 2x to the power 5 over 2 plus x to the power 3 over 2 minus 3x to the power 5 over 2, 1/2 plus 2, 5 over 2 minus 3x to the power 3 over 2 over the denominator, which is positive, and I don't care about it because it's positive, right? This moment, so this is negative x to the power 5 over 2 minus x to the power 3 over 2. Now recall that x in this case it's always positive. Why? Because it represents, this function just represents this sequence when the function is evaluated at the integers, and we talk about positive integers only. So for positive x, because the numerator is negative obviously and the denominator is positive, this is less than 0, which means that Pn is decreasing. And by the alternating series test, we can conclude that this series is convergent.